Hello students, welcome to our class Mechanics of Materials. In today's lectures, I am going to discuss material property relationship. In our last class, we have discussed strain transformation, and I missed one thing in that lecture. So I want to introduce this first before starting the today's lectures. So as I said that like a stress transformation, you can do the planes transformation, and you can also draw a more circles for plane strain condition. So this is the circle which can be drawn as I shown in my last two classes for the stress transformation, and it will be you can do a more circle for the plane strain following the similar approach as I discussed for the more circle for the plane stress. Now, so in today's class, as I mentioned in the beginning, I'm going to start with the material property relation. So so let's start with this one. And so all we know the Hooke's law. Remember the Hooke's law? The Hooke's law said Hooke's law, if this is an element and it has a one-dimensional stress here, normal stress, then for the Hooke's law, sigma is proportional to stress is proportional to strain. Stress is proportional to strain. And if I use a proportional constant, this is E epsilon, where this is my elastic modulus, this is strain, okay, and we also learned at the last also learned Poisson's ratio. Okay, Poisson's ratio, nu equal to minus lateral strain, longitudinal strain. Ratio of Poisson ratio is the ratio of lateral strain and the longitudinal stress. Now, so this equation can be used for one dimensional object. Now, what would be, now think about a scenario that you have an 3D object, 3D element, and you have an element which is and this element is subjected to three normal stresses. So if this is my coordinate, this is my y coordinate, this is x coordinate, and this is z coordinate. So this is sigma y, this is sigma x, and this is sigma z. Okay. So what is the form of Hooke's law for these tri-axial stress state. What is the form of Hooke's law for this tri-axial stress state? So we have this is a 3D element and it experiences sigma x, sigma y and sigma z stresses. Now we're going to do step by step. First, let's consider say sigma x. Okay, so sigma x is applied in x direction So now if I, for the simplification, if I take this face for example and draw this face, and this is my sigma x is acting on both sides. Okay, sigma x, sigma x. Okay. Now this sigma x, when it acts on the x direction, what is the, so this face is going to elongate in x direction. Okay, so the element because of the sigma, the x stress, the element elongates in x direction, right? Sigma elongates in x direction. Okay. Sigma elongates in x direction. Okay. Now, but contrast in z direction. Let me try to explain this. So remember, this is my x and this is my z. If I take this face, just try to imagine, so it elongates in sigma x. When sigma is applied in the x direction, elongates in the x direction, but contrast in the z direction. So this green line, green dotted line, is the represents the element after deformation. Now, so we can say sigma x causes epsilon x prime strain in x direction. Okay, so we can write the Hooke's law, sigma x equal to Young's modulus multiplied by this will be epsilon prime x. Okay, this is, and then if we rearrange this, we can say epsilon prime x equal to sigma x divided by, so this is our equation number 1. Okay. Now consider sigma y. So I'm drawing this again. Okay. So now sigma y, this is my sigma y, okay, and sigma y, and this is my, remember my original coordinate y, x, z. Sigma y is applied in y direction. Okay, so let's consider this face. Okay, if I draw this face here, and this is my sigma y, okay, now this sigma y so this is the new deformation. So again, what is the coordinate here? Here this is my x, so this is my y, and this is my x. Okay, so I'm considering this face, the top face. Now, so as I said, sigma y is applied in y direction. As a result, the element contracts in x direction but the element contracts in x direction, right? And so we can say sigma y causes epsilon double prime x strain in x direction. Okay, and epsilon y strain in y direction. Okay, so if I write the Hooke's law here, I can say sigma y equal to E epsilon y, right? Again, from the Poisson ratio, we know nu is equal to minus lateral strain. In this case, our lateral strain is epsilon prime x and epsilon y is our longitudinal stress. So if we rearrange this, we can say epsilon y equal to minus epsilon double prime x by nu. Now if I plug here sigma y, if I plug epsilon y into epsilon y here, so sigma y is equal to E minus epsilon double prime x by nu. If you do the rearrangement, we can write epsilon double prime x equal to minus nu sigma y e. So this is my second equation. Okay, so now consider the last stress. The last stress is sigma z. So again, this is my coordinate, this is y, this is x, this is z. So this is the element, okay, and sigma z is acting. Now if I take this face, now sigma z is applied in z direction. Sigma z is applied in z direction. Now if I take this face for the simplification, what can I write? So this face, okay, and the coordinate here is for this face, we write in 2D, this is my x, this is my z. Okay. Now this is sigma z. And because of the sigma z stress, this element deform like that. That means it elongates in z direction but contrasts in I made a mistake. So let me rewrite this. So it's gonna be z is gonna be x. Okay. That means let me do this again. So if these elements, say this is my z, sigma z, okay, and this is my z coordinate, and this is my x coordinate. Okay. So what happened when I pull these things element, is gonna be elongated in z direction, is elongated in z direction, and this is z direction, but it contrasts in x direction. So we can write that sigma z causes the element to contracts in x direction and sigma x causes epsilon 3 prime x strain in x direction, and epsilon z strain in z direction. Okay. So we can write the Hooke's law, sigma z equal to E Young's module multiplies by epsilon j, normal strain, right? Again, according to Hooke's law nu, we can write minus epsilon 3 prime x epsilon z. So what I'm writing here is epsilon nu is equal to excuse me, lateral strain divided by longitudinal stress. So if I rewrite this, I can write epsilon z equal to minus nu epsilon 3 prime x, sorry, minus epsilon 3 by x nu. Now if I replace this here, sigma z is going to be minus E epsilon x triple prime x divided nu. If I rearrange this, epsilon triple prime x is minus nu sigma z e. Okay. So we got three strain: epsilon x, epsilon y, and epsilon z. Now, second, let me repeat. We got three strain. We got three strain in x direction. Okay. So what is these three strain? Epsilon x, epsilon double prime x, epsilon triple prime x. So epsilon x is equal to sigma x divided by e. This is our equation number 1. Epsilon double prime x is equal to minus nu sigma y divided by e. That is equation number 2. And epsilon 3 prime x equal to minus nu sigma z divided by e. So these three equations we got so far. Now, so the strain, because it's, let me see, it is either contracts or expand, so we can actually superimpose strain epsilon x, epsilon double prime x, epsilon triple prime x can be superimposed, to find the normal strain epsilon x. So epsilon, so this is epsilon x prime, sorry, so x, okay. Epsilon x. So epsilon x equal to epsilon x prime plus epsilon double x prime plus epsilon triple x prime. Now that means we are going to add equation 1, 2 and 3. If I do this, sigma x e plus minus nu sigma y e plus minus nu sigma z e. Now if I take this 1 by E out, take common, then I can write sigma x minus nu sigma y plus sigma z. So this is my epsilon x. Similarly, the similar way we can actually derive epsilon y, and it is going to be 1 over E sigma y minus nu sigma x plus sigma z, and epsilon z is going to be 1 over E sigma z minus nu sigma x plus sigma y. So these three equation expresses Hooke's law in general form for a tri-axial state triaxial stress state. Triaxial stress state. Now, so these three equations is valid for a 3D element, and that element should be subjected to three different normal stress: sigma x, sigma y, and sigma z. Now, so we know that Hooke's law is also valid for Hooke's law is also valid for shear strain. We know the shear stress tau equal to shear modulus shear strain, right? We have learned this before. And for the 3D element, we can actually write, for the 3D element, this is gonna be our if a 3D element is subject to a shear stress, for example tau xy, it will deform like that. Tau yz, it will be deformed like that, and tau xz is going to be deformed like that. So Hooke's law for these three different stress states, there are three different Hooke's law that actually correlate shear stress and shear strain. So I'm going to write these three stress strain relation. So Hooke's law for shear stress and shear strain. Gamma xy equal to 1 by z tau xy, and gamma yz equal to 1 by z tau yz, and gamma xz equal to 1 by z tau xz. So you can find all the equation I wrote so far in the book from page number 512 to 513, and the next topics I'm going to teach is dilation. Now before move to the dilation, so remember we so far we introduced two modulus. One is elastic modulus and the another one is, and it is denoted by E. The another one is shear modulus. It is denoted by G. So there is a relation between E and G, and the relation is Z equal to E divided by 2 1 plus nu, where E is your Young's modulus and nu here is Poisson's ratio. Poisson's ratio is your elastic, nu is defined by that. So now, as you know, so this relationship is very important, and it is important because sometimes you need to figure out what is the shear modulus, and you can easily calculate it, the shear modulus, if you know your elastic modulus and Poisson's ratio. So the next topics I'm going to cover is excuse me, is dilation. So the dilation is let's consider an element. Next topic is dilation. Okay. So let's consider an element. Okay. And this element this is dx sorry, this is dy, this is dx, and this is dz. So before applying any load on this element, the volume of this element is say dV old, and it is dx, dy, dz. Okay. Now next I applied stress on this element. I apply stress on this element. Okay. Now this length is changed 1 plus epsilon y dy, and this length is 1 plus epsilon x dx, and this length is 1 plus epsilon z dz. Okay. So our new volume dV new is multiplication of these three new lengths, say 1 plus epsilon x dx, 1 plus epsilon y dy, and 1 plus epsilon z dz. Okay. Now the change in volume of the element is delta V, and this delta V is nothing but dV nu minus dV old. Okay, so what is the dV nu? If I dV nu, I can say dV nu here is 1 plus Ex, 1 plus Ey, 1 plus Ez dx dy dz minus dx dy dz. Okay, So this is my delta V. So I don't go the details. I'm not going to go to the details of this calculation, but what I am trying to say, if we ignore the multiplication of delta x delta y, so if you multiply these things, you will see there will be a lot of there are four terms will come out is epsilon x, epsilon y, epsilon z, epsilon x, epsilon x, epsilon y, epsilon z, and epsilon z, epsilon y. So if you ignore the multiplication of the strains, and we can ignore this because epsilon itself, epsilon x, epsilon y, epsilon is a small number. When you multiply the two small numbers, they get even smaller. So the final form we will get from here is delta V is going to be epsilon x plus epsilon y plus epsilon z dx dy dz. Now this term is actually what? dv. We can write delta v is equal to epsilon x plus epsilon y plus epsilon z dv. So delta v by dv, we can say summation of strain in three direction. So this delta v by dv is a indication of volumetric change. So we can say change in volume per unit volume. Change in volume per unit volume. Change in volume per unit volume. And this change in volume per unit volume is known as dilation, and this dilation is denoted by E. So the E equal to epsilon x plus epsilon y plus epsilon z. Now there is another famous formula which correlates the dilation and the stress, and that is E equal to 1 minus 2 nu E sigma x plus sigma y plus sigma z. So this formula, this one, is the correlation between dilation and the strain, and this formula correlates dilation with the stress. So this is actually relation between dilation and stresses, and this formula is dilation, correlation dilation and strain. Okay. Now think about a scenario where your element is subject to compression in all directions, all the faces normally, and if you have this, if this element is submerged in water, in a liquid, and it experiences pressure in every direction, x, y, z. So we can write this sigma x, sigma y, and sigma z. So when a volume element is subjected to a uniform pressure, P of a liquid, we can write sigma x equal to sigma y equal to sigma z equal to minus p. It is negative sign because it is in compression. The element is in compression. Now use this equation. Say E equal to 1 minus 2 nu divided by the small e, 1 minus 2 nu by E caps E all, and this is Young modulus, and we replace sigma x, sigma y and sigma z with p. So this is minus p, minus p, minus p. Excuse me. So E is 1 minus 2 E to 2 nu divided by E. So we can write minus 3 p. And if we rearrange this, we can write P by E equal to minus E 3 1 minus 2 nu. Okay, and this P by E is analogous to Young's modulus sigma by strain. So remember, sigma is analogous to pressure, and volumetric strain or dilation E is equal to E is analogous to normal strain E. So we can say this is K E 3 1 minus 2 nu. Okay, and this K This K is known as bulk modulus, and also or volume modulus, so volume modulus of elastic, okay, volume modulus of elasticity. So it is also, this bulk modulus is extensively used in engineering. So I hope after today's class you get the idea what is the bulk modulus. Bulk modulus is actually volume modulus of elasticity, and you can easily correlate, you can easily find the bulk modulus from the Young's modulus and the Poisson's ratio. So if you know your Young's modulus or elastic modulus and the Poisson's ratio, you can easily calculate the bulk modulus. So next we are going to solve an example problem. So the example problem we are going to solve is example 10.10, and it is in the book page 518. In the book page 518. So in this problem, a copper bar is subjected to a uniform loading along its edge as shown in figure, and the copper bar has a length A is equal to 300 millimeter, width B is equal to 50 millimeter, and thickness T is equal to 20 millimeter before the load is applied. So if you see that this copper bar is pulled in this direction, in horizontal direction, and it was pressed in vertical direction. So we can say this bar is a subject to a plane stress. Now in order to solve this problem, we will be using the generalized Hooke's law I discussed today, and we derived those generalized Hooke's law. So we simply draw a 2D of this bar, draw a 2D version of this bar, and we say that this is 800 megapascal. Okay, it is pulling this bar, and this is 500 megapascal, and this is my coordinate. The horizontal axis is X and the vertical axis is Y. Okay, now let's use this pen. Now so I use the Sanka machine. The sigma x equal to 800 megapascal, right? Because the element is in the copper bar is in tension because of this 800 megapascal, so it is positive. And sigma y is minus 500 megapascal. Okay, and this 500 megapascal actually is used to compress this bar, so that's why it is negative, and we do not have any stress in z direction, that's why it is 0. Now it is given that Young's modulus of the copper is 120 gigapascal, so which is 120 10 to the power 9 Pascal, and Poisson's ratio nu is given 0.34. As we know, the Poisson's ratio doesn't have any unit. So the first step to find the elongation or contraction, the change of length in the length direction, width direction, and the thickness direction, we need to find the strain in all directions. So let's first start with epsilon x, strain in x direction. So this is the generalized Hooke's law, 1 by E sigma x minus nu sigma y plus sigma z. Okay, this is what we learned from our today's lecture, sigma y plus z. Okay, and now the next we are going to plug this value. So 1 by E, we know E is equal to 120 into 10 to the power 9 Pascal. Sigma x is 800 megapascal, so we can write 10 to the 6 Pascal minus nu is equal to 0.34, and sigma y and sigma z, sigma y is equal to minus 500 and sigma z is equal to 0. So this one we can write, and that should be 10 to the power 6 Pascal. Okay, so our epsilon x is, if we do the calculation correctly, it is 0.00808. Similarly for epsilon y, our governing equation is 1 by E sigma y minus nu multiplied by sigma x plus sigma z, which is 1 by 120 into 10 to the power 9 Pascal. Sigma y is minus 500 megapascal to the 6 Pascal minus 0.34, and sigma x is 800 megapascal and sigma z is equal to, as we know, 0, so equal to 800 into 10 to the power 6 Pascal. And if you calculate this, going to be minus 0.00643. Okay. Now our normal strain in z direction is, equation is 1 by E sigma z minus mu sigma x plus sigma y. So here sigma z is equal to 0. We can add 1 by 120 10 to the power 9 Pascal and minus 0.34, and sigma x equal to 800 minus 500 megapascal 10 to the power 6 Pascal. So if I calculate this correctly, this is even smaller, 0.000850. Okay. Now, as we know that the normal strain epsilon x, we can write is a prime, the change of length, the new length a prime minus original length a divided by original length a. So it is given here. So let me tell you that given that your a is 300 millimeter, so we can write a prime minus 300. Okay, so okay, let me do this way, forget this. So if we rearrange this, is going to be a prime plus a epsilon x. So we know a is 300 millimeter plus 300 millimeter multiplied by 0.008 803. Okay, now if I, so my a prime is going to be 302.4 millimeter. Okay, now again we know that epsilon y is b prime minus b, we can rearrange, is b prime, the new width, b prime is the new width, is equal to b plus b epsilon y is equal to 50 millimeter plus 50 millimeter multiplied by minus 0.00643. Okay, so So B prime is 49.68. B prime is 49.68 millimeter, and epsilon z is new thickness minus original thickness T divided by original thickness T. So we can write T prime equal to T plus T epsilon y, which is, and from the questions we know T is 20 millimeter. T is 20 millimeters given. So 20 millimeter plus 20 millimeter multiplied by minus 0.000850, and so T prime is 19.98 millimeter. So these is the three new number we got. So the new length is 302.4 millimeter. The new width is 49.68 millimeter, and the new thickness is 19.98 millimeter. So you have done this kind of problem in 1D. So today we have learned how to solve the change of lengths, or how to solve the deformation of a 3D object and find the new lengths. So this problem is an example 10.10 in you can find this in the book in the page number 518. So please watch these lectures and try to understand the relations between the material property, and you need to understand the relation between the different moduluses. For example, elastic, shear, dilation, or the bulk moduluses. And because actually most of the problems in the real engineering problems in many occasions is this 3D. So we need to understand how the Hooke's laws and the Poisson's ratios, other everything can be implemented in 3D. So I hope after today's class you were able to apply the Hooke's law in an object, 3D object, which is subject to tri-axial stress test. So thank you very much for watching, and we will discuss about the finals and other things in our next classes. Thank you very much.